In section 2.2, we're going to take the concept of a frequency distribution and begin to apply it to visual representations of our data. Specifically, though, in section 2.2, we're going to be taking a look at quantitative data. That is, data whose values are actual measurements, okay? Not quantitative, but qualitative. I'm sorry, not qualitative, but quantitative, actual measurable data points. Okay? So the first of these visual displays of data that we're going to take a look at is called a histogram. The histogram is a graph that displays the data by using continuous or contiguous vertical bars, unless the frequency of a class is 0. We'll see that, or what that implies here in a moment, of various heights to represent the frequencies of the class. So let's take a look at an example. We have an example here. It says, construct a histogram to represent the data shown for the record high temperatures for each of the 50 states. So each of the 50 states, it looks like 2 of the 50 states have record high temperatures of 99.5 up to 104.5. 8 have a record high temperature somewhere between 104.5 and 109.5. Notice these are class boundaries. They took into account the fact that temperature can take on a ratio level measurement. What do we mean by that? Decimal or fractions between whole numbers. Right? There's an infinite number of values between 99 and 100. The temperature could take on any one of those infinite values. So we have to institute class boundaries. And then we continue to move forward. 18 of the states had a record high temperature somewhere between 109.5 and 114.5. And it goes down from there, or the temperatures go up from there, and we see the frequencies for each of them. So what are we going to use? How are we going to use this data to construct what is called a histogram? So in a histogram, we have a vertical and we have a horizontal axis. The horizontal axis is always our classes. What we're going to find out is they are our class boundaries. Now, specifically for us, it is going to be temperature in degrees Fahrenheit. So notice I'm using the unit of measure, what we're measuring, and the unit that we're measuring in. Okay. The vertical axis is always going to be your frequency in a histogram. So how do we set this up and how do we construct the histogram? It says again that the histogram is contiguous vertical bars. So we're going to have a whole bunch of vertical bars right next to each other that show their relative size or their relative frequency to every other class. Okay, so here's how this is going to work. On my horizontal, I am going to end up putting my class boundaries. My first class boundary is 99.5. So I'm going to make a mark and go 99.5 all the way up to 104.5. But then my next class goes from that 104.5 up to 109.5. And then from 109.5 up to 114.5. And then from 114.5 up to 119.5. From 119.5 up to 124.5. And from 124.5 up to 129.5. So notice I'm using all of these, but then we have to cap it off with the 134.5 here at the end. So what I've done is I've sectioned off in equal widths my lower and upper class limits. Or I should say, sorry, class boundaries. Now what I'm going to do is I'm going to take a look at my frequencies, and I notice my largest frequency is 18. So my vertical axis needs to go up to at least 18. I'm going to say let's go up to 20. And I'm going to count by twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now what I'm going to do is I'm going to take a look at each of my classes. My first class from 99.5 up to 104.5, which is this section right here, has a frequency of 2. So I'm going to draw a bar that goes up to 2. Now my 104.5 up to 109.5 has a frequency of 8. That's up here. My next from 109.5 up to 114.5, this is where it jumps up to 18. And then my next class, 114 to 119, is a frequency of 13. And I'm going to continue this through the end. Now it's 7. It's about right here. Obviously, drawing by hand, things are not perfect. And then we have 1 and 1 here at the end. So what has this done? Well, it's given me a visual representation of what my data looks like. In the next chapter 3, we're going to be drilling in more on these things called measures of center and measures of spread. But this visual already gets us kind of this good idea of center and spread. The vast majority of states, right, have a max temperature somewhere here between 109.5 and 114.5. But then you can see that even though that's the majority of states are somewhere in that range, we also have states that go down as low as 99.5 and as high as 134.5. So it kind of shows me where my data is centered at, as well as where my data is spread out on each side of that center. It gives a really nice visual description of the data that we have here for max temperatures in each state. So there's our histogram. Now there was that comment right here, unless the frequency of a class is 0. Notice that we always construct things so that all of our bars are right next to each other. The lower and upper boundaries of neighboring classes are the identical values, so they should be next to each other. But what if we had a class, let's say instead of this being 8, this was 0? Well, this would just disappear. What that means is when there's a gap between two vertical bars, and because of it's 0, that's actually significant. It means that nothing actually was in that class. So keep that in mind. Okay, the next chart that we want to take a look at is very similar in concept, but we're going to make a few adjustments to it. It's this thing called, instead of a histogram, a frequency polygon. It's a graph that displays the data by using lines rather than bars that connect points plotted on the frequencies at the, here's the key, midpoints of the classes. The frequencies are represented by the heights of the points. So what we actually need to do, you'll notice here they've already done that in this chart, is we're actually interested in midpoints of these classes. How do you find the midpoint? Well, to find the midpoint of a class, you add the lower 99.5 and the upper 104.5 together. Let's see, that's a 10, that's a 14, that's a 10 and a 2. So 204.0. And then what are we going to do? We're going to take that 204 and divide it by 2. 2 goes in that 1, 2, so 0, 0, 0, 0, and then the 4 drops down twice, 4, and that ends up being 0. So my midpoint, look at that, we got what they got, 102. It's halfway between my lower and upper boundaries. Okay? Well, what did we just do? All we did was find the average of the upper and lower boundaries. That's how you find your midpoint. You add the two together and divide by 2. Okay? So midpoints become really important when we're constructing these things called frequency polygons. Here's how we construct the frequency polygon. We still have our vertical and horizontal axis. The vertical axis still is frequency. Okay, we're using the same data, so I'm going to count by 2s again. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. But instead, down here of my class boundaries for temps, or for my temp in degrees Fahrenheit, I'm actually going to put the midpoints. So 102, 107, 112, 117, 122, 127, and 132. Now what I'm going to do is I am going to put a point, not a bar, but I'm going to put a point at each of these midpoints associated with its connected frequency. So the midpoint of 102 for this class boundary had a frequency of 2. So at 102, I'm going to put a point at 2. Okay. At 107, I'm going to put a point at 8. For 112, I'm going to put a point at 18. For 117, I'm going to put a point at 13. Let's see if we can get as close as possible. And then at 122, we're back down at 7, and then a 1 and a 1. Now that I've plotted the frequency connected with the class's midpoint, I'm simply going to take these and I am going to connect them. But there's one other critical thing here. I'm actually going to make a point down here at 0 where the midpoint of a class right below this would be. So then I'm going to start connecting my frequencies connected to my midpoints. And then I'm going to drop this off back down to 0 again. This is a frequency polygon. Okay, so you can see the flow of frequencies referenced to the midpoints of each class rather than using bars to represent the height of each class's frequency. Just a different way to communicate visually the same exact data, the same exact information. The next one that we want to look at is this thing called an ogive. Ogive, there's a bunch of ways people pronounce it. But an ogive is a graph that represents the cumulative, these is key words right here, cumulative frequencies for the classes in a frequency distribution. So continuing to work with the same data that we have right here, right, take a look at what they've got going on here. And we got our class boundaries, we've got our midpoints, and we've got the frequencies. But in order to construct an ogive, what does it say we need? We actually need cumulative frequencies. So what that means is this. Instead of taking a look at each class and the frequency of each, what we're going to do is we're going to take a look at each class and we're going to add the frequency of the current class to the frequencies of all classes before it. You'll see that here in this chart and how they did that. Notice what they did is they took the lower boundaries and they started off by saying this, okay, how many values are there less than my lowest boundary? So less than the 99.5. Well, we know that's going to be 0, right? And we do that on purpose. So we take the first class, the lowest boundary, and we say less than 99.5. Okay? And that's going to be 0. But then we take the next lower boundary of 104.5 and we ask ourselves, how many data values are less than this? Well, this is the upper boundary of the class before it. Well, how many data values are there less than 104.5? Well, there's 2 less than 104.5. Then, that's where we get the 2 here. Then it says, well, let's go up to the next one, the 109.5. How many are less than 109.5? Well, the 2 that we already had here, but then the 8 that we have here. What is that total? That totals 10. So again, we're not looking at a specific class. We're looking at a boundary and asking ourselves how many data values are less than that boundary. In other words, all you're doing is you're taking your frequencies up here and saying 2 plus 8 is 10. Or we started off at 0. 0 plus 2 is 2. That was here. 2 plus 8 is 10. 10 plus 18, that's where your 28 is coming from. 28 plus 13, that's 41. 41 plus 7, that's your 48. 48 plus another 1 is 49. And 49 plus another 1 is 50. Notice your very last value in your cumulative frequency should equal the total number of data values. It should equal all of these added up. And in fact, it does. Okay? So an ogive is constructed using this concept of a cumulative frequency. It's a everything, how many data points are this value, or rather less than a specific value. Okay? Now what we're going to do is, just like a frequency polygon, we're going to connect several dots with lines. Again, here's going to be our frequency. Now we got to be careful here because this is our cumulative frequency. And notice that my cumulative frequency goes up to 50. So I'm actually going to count by fives. 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And then down here we still have temp in degrees Fahrenheit. But now what I'm going to do is I'm going to put all of these less than boundaries. So 99.5, 104.5, 109.5, 114.5, 119.5, gonna have to extend this out, 124.5, 129.5, and 134.5. Now, where do I start? Less than 99.5, 0. So I'm actually going to put a point right here. Less than 104.5, I'm up at 2. Less than 109.5, I'm up at 10. Less than 114.5, I'm up to 28. Less than 119.5, I'm up to 41. It's about right there. And then my next one is 48, and then 49, and then 50. So we've plotted all of our cumulative frequencies based on the less than specific value of a class boundary. Now what I'm going to do is I'm simply going to connect all of my dots with a line. And this, now we have constructed an ogive. Okay? An ogive specifically communicates the cumulative frequency, not the frequency of each individual class, but the frequencies of each class continuously added onto each other until you get up to all your data values. Great. We do have one more concept that we want to take a look at in context of all three graphs we've seen, the histogram, the frequency polygon, and the ogive. Okay? And we want to take a look at them in the context of what is called relative frequency graphs. Relative frequency graphs for a histogram, for a frequency polygon, for an ogive, all constructed the same. Notice with the histogram, okay, we have our class boundaries right here, and then the height of each of these is going to be some sort of frequency, but a different type of frequency than what we've been working with. Again, here we found the midpoints, and we put a dot at the midpoints, which represent something called a relative frequency instead of just a frequency. And then last but not least, the ogive. Again, notice it's cumulative frequencies, again, at the less than lower boundaries of all of our classes. Okay, but how did we get this concept of a relative frequency? Well, here's how we did it. It actually comes from something we did in the previous section, section 2.1. We asked ourselves percentages. Okay, we asked ourselves percentages. So what do we mean by that? Okay, what we mean by that is I know, looks like from my frequency distribution, I have a total of 50 values. And in this first class of 42.5 up to 47.5, we had 4 total values that fit into that class. Well, a relative frequency is what percentage of my data does that represent. Relative frequency is nothing more than percentages. Okay? But we're going to represent the percentages as decimals. So 4 out of 50. So literally 4 divided by 50. Well, 4 divided by 50 gives me 0.08. Now, 4 again divided by 50, 0.08. And real quick, if we work through this, 11 divided by 50 gives me 0.22. 14 gives me 0.28. 9 gives me 0.18. 5 divided by 50 gives me 0.10. 3 divided by 50 gives me 0.06. If I were to add all of those up, I would end up at 1, or 100%. Now take a look at what's happening over here in the histogram. We constructed the horizontal axis just like we did above in the histogram. But notice my vertical axis, instead of frequency, where I'm plotting these values, it's relative frequency. I'm plotting my decimals, which represent percentages. So from 42.5 to 47.5, I'm not plotting a frequency of 4, I'm plotting a relative frequency of 0.8 right here. And then another 0.8 for my next class, 0.22 here, 0.28 here, 0.18 here, 0.1 here, and 0.06 here. So the only difference is, instead of constructing it using frequencies, I'm constructing it using decimals, which represent the relative frequency. What this class represents, what percentage of the data represented in decimal form. And you can see the same thing here in the frequency polygon. They found the midpoints of each of these classes right here. And then they took those same, instead of the frequencies, oh, look at that, here's the relative frequencies that we found right here. Okay? And instead of the frequencies, they're plotting the relative frequencies on the vertical axis. And last but not least, an ogive. Right? Instead of plotting, notice we have the less than is still what our horizontal axis is, the less than those certain boundaries, but then my cumulative frequencies, we calculated those, but then take a look at what happens. We know that we have a total of 50 values. Well, 0 out of 50 is 0%. 4 out of 50 is 8%. Right? Now there's 8 values that are less than 52.5. 8 out of 50 is 16%. 19 values are less than 57.5. That's 38%. And notice with this, and this is the way it should always work when doing relative frequencies with an ogive, is the last value should always be 1, which represents 100%. Because at that point, you should get to a point where all of your data is less than that last value that you use. So we're plotting cumulative relative frequencies at the associated midpoints for the ogive. Last concept in section 2.2 is this concept of distribution shapes. Distribution shapes are typically viewed in the context of a histogram, the very first chart that we looked at. And there's a few in here that are going to be the most critical to us. This term is going to come up a lot in the rest of this course, bell-shaped. Notice in this that we have this really nice shape of a buildup of data to this center point that then fairly symmetrically dives off on the other side, so that each side looks fairly closely to a mirror image of each other. All right, we call that bell-shaped, when there's one peak in the middle and both sides taper off fairly symmetrically. When all of our bars on a histogram are relatively the same height, we call that a uniform distribution. Now, sometimes we have data where it starts low and then it just keeps building all the way up to the other side. We call that J-shaped. And if it's the opposite, where we start high and everything kind of tails off this way, we call that a reversed J shape. Okay. Next, we have what are called skewed distributions, skewed left and skewed right. These look similar to this whole bell-shaped curve up here in that there looks to be a peak here and here, but in this case, the right side seems to take longer to taper off than the left side. In other words, that right side looks stretched out, so we call that right skewed. Over here, this is my peak, and it looks like the left side is stretched out. We do have something that dives off on the right side here, but the left side kind of stretches itself out and takes longer to dive off. We call that left skewed. And last but not least, these last two right here, fairly related to each other. If we have data where it looks like there's two different peaks that taper off on each side, we call that bimodal. And lastly, if we have it where we have scenarios where our largest values are on the very ends of our histogram and it dips in the middle, we call that U-shaped. So just be aware of these. The ones that are going to come up the most is bell-shaped, and then the skewed left and skewed right shapes. Those are the ones that we're going to end up talking about the most as we continue in this course.